So this could be a terrible presentation. And like I said, I don't know that I taught this one last year. I don't know if it's new or if I just saw it previous years and I was like, let's skip over that. But we've already gone over this a little bit because we have learned about Mendeleev. We watched the video about Mendeleev and how he kind of helped develop the periodic table alongside some other people. And so we're going to talk a little bit about him. We're going to start with the early periodic table. Then we go to Mendeleev, and then we go to the modern periodic table, and they kind of have all the information summarized for you on the sheet. So let's get going. In the 18th century, without modern scientific equipment, without knowing about protons or neutrons or electrons or really anything about atoms, they started to try to make a representation of all the atoms that we knew about. Because we knew, not atoms, of elements that we knew about. We were aware of elements. We were aware of like gold and silver, and that you could make alloys of different metals and mix them together and get different properties. Even in the 18th century, we were developing early medicines and figuring out what kind of chemical reactions happen in your body to do different things. So we understood a little bit about elements and how they worked and how you combine them. But we didn't really understand atoms as a whole or why these things did what they did. So without modern scientific equipment, scientists had a limited ability to perform experiments. Many elements were still undiscovered for thousands of years. And during the Enlightenment age or era, the amount of scientific experimentation increased. So we found additional elements. We discovered new things. And Antoine Lavoisier published the first chemistry textbook in 1780s. And actually, the video that we watched about Mendeleev talked about Antoine Lavoisier and his first periodic table and how he got to that point a little bit. So it listed 23 elements. Which did anybody grab a periodic table today? Well, yeah, I gave you one. Okay, fair enough. How many elements are on the periodic table now? What's the biggest one? 118. So we have 118 elements right now today. To be honest, we might increase that number in the future. I think everybody kind of thinks that we got it squared away, but there's a lot of weird stuff out there. You never know what could happen. So they only knew about 23, which is not even close to like a quarter of it. They still have a lot of elements to discover. And so to be fair to Antoine Lavoisier and the first people that created periodic tables, it would be difficult to put a chart together without having all the pieces. It's like trying to assemble a puzzle with only like a quarter of the pieces, and you don't even know what you're missing. That would be extremely difficult. So in his textbook, he listed the 23 elements, detailed pictures and descriptions of experiments he used to isolate each of the elements and get them kind of in their pure form so he could study them a little bit more and do experiments on them. By 1869, there were 63 known elements. So that jumped pretty quickly. Lavoisier was 1780s. So in less than 100 years, we had almost tripled the amount of elements that we knew. We went from 23 to 63. So we're kind of snowballing here and discovering more and more stuff and figuring out how to look for these things and to kind of organize them. So Mendeleev comes along, Dmitry Ivanovich Mendeleev. He organized the elements by atomic mass and chemical reactivity, and that's the most important thing. You have that on your modern periodic table. Their modern periodic table today. They're organized by their number of protons, which, if you look at the atomic mass in the bottom squares of these periodic tables, it does go in order. Hydrogen is lighter than helium, it's lighter than lithium, and as you go up, they just get heavier and heavier and heavier because the more protons you have, the more neutrons you need to be stable. So it just kind of follows that atomic mass idea. Now, Mendeleev still did not understand the idea of subatomic particles with protons and neutrons or anything like that. He was just taking the elements and weighing them and trying to figure out their relative weight. So they're organized by atomic mass, and he noticed certain elements had similar chemical reactivities. They like to combine with other elements. And we haven't really talked about this yet, but this is what we're leading into. We're getting there. So he created the first widely accepted periodic table, and this is actually it. Notice you got a lot of missing pieces here. All the places you see the dashed lines is an element they have not discovered yet. But Mendeleev was one of the first people to say, hey, I will admit that there's stuff missing here, that I don't know every single element that there is. These 63 aren't the end of the list. Where everybody before had just tried to fit it all in and say, well, this is what we know out. There's really nothing else. He was like, no, there's a space here in my chart, and that space means that there's an element there. We haven't found it yet, but this is the way that it works. This periodicity, it just keeps repeating itself over and over and over. And if there's a gap, that's not because there's that element doesn't exist. It's because we haven't found it yet, which is very, very important for the development of the modern periodic table. So we found patterns by arranging cards with names of masses and other physical and chemical properties of the elements. He saw that all of your alkali earth metals in the orange behaved exactly the same. Even though they were different masses, they behaved in very similar patterns, and they would always want to combine with your halogens on the other side of the periodic table. He didn't know why yet. It took us quite a while to figure that out, but he did know that they reacted in the same way with all of the halogens. It didn't matter what their mass was. It was their physical and chemical properties. He placed the elements into number groups based on similarities in combining power. So he's looking, like I said, how they react with other elements on the periodic table. If they don't react with a certain column, but they do react with another column, that's important. And he was one of the first people to kind of understand that and emphasize that. So alkali metals, which, like I said, are your orange ones, had combining power of 1 and went in with group 1. So we still have those listed as group 1 today. They have the groups all the way up at the top here, 1 through 18, which, by the way, is 2 plus 6 plus 10 are different sections of the periodic table, S, P, and D. So alkali earth metals had combining power of 2 and went into group 2. So alkali earth metals are your yellow ones. Alkali is the orange, alkali earth metals are the yellow, and so on and so forth. Properties of some elements did not fit when arranged by atomic mass. Properties of some elements indicated that more massive elements should come before less massive ones. They didn't know about isotopes at the time. They still didn't know about protons or neutrons, so they didn't know that there were elements of the same, or atoms of the same element that weighed different amounts. And that kind of threw off their order of mass as they moved their way through the periodic table. So Mendeleev relied more on the properties, the similarities of the properties, than the order of the masses to arrange his elements, which was a huge breakthrough. And like I said, he was really the first person to leave those blank spaces for elements that had not been discovered, and claim that that is an element. It's not just a gap. It's not just a coincidence. That is an element that we haven't figured out. And he even tried to predict what those elements were. Predicted the chemical reactivity and masses for gallium, scandium, and germanium, even before they were discovered. So after Mendeleev's table was published, inert gases were discovered. We didn't know about the, my brain just blanked out, noble gases all the way on the right, because they don't react with anything. Like I said, when we talked about the Lewis dot structures and that rule of 8, that all the electrons want to get to that 8th electron in their outermost shell, noble gases have 8 electrons. They're non-reactive. They don't want anybody's electron. They don't want to give away any electrons. They can bump up against all sorts of other atoms and never combine, never form any other elements. And they're all gases. So you're not just going to find like a clump of it in the ground and be able to like analyze it. It's just floating around in the air around us. So it took us a long time to find these: helium, neon, argon, krypton, xenon. Those are your noble gases. Now, the new group was made at the end of the periodic table, which was nice and easy because we just like threw it on the end. It didn't have to be inserted anywhere or change it all that much. And let's see. Yeah, this is pretty similar to what we have going on. We got helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, all the top row right there. They just didn't know about the noble gases at the time. Named the zero group since they did not react and had combining power of 0, which is not what they're named today. They're just the 18th group all the way at the very end. So fast forward a little bit, 40, 50 years, 50-something years. In 1914, Henry Moseley's work with X-rays showed that each element had a unique positive charge in its nucleus. So now we're starting to understand the number of protons. So every single element has a different number of protons in the nucleus, and that's what makes it unique. If you change the number of protons, you change the element and what its properties are. So positive charge was the result of the number of protons, and they labeled it the atomic number because literally it's the most important thing. It's what creates your atom and makes it unique in that way, is the atomic number. So Moseley arranged the periodic table by atomic number instead of atomic mass. He fixed some problems that had occurred when organized by the mass and used the atomic numbers. The use of atomic numbers confirmed the existence of elements such as technetium. Technetium, where's technetium? Maybe down here in the...
What's the symbol?
I don't know. I'd imagine it starts with a T, but that's not guaranteed.
TM, number 69.
TM 69. No, that's thulium.
It's 81?
Technetium.
81?
Where I'm looking.
For sure.
GI, 3A, bottom?
No, it says technetium. I don't know what technetium. Promethium. Where's promethium?
PO,
59. PR, 59.
It's 59.
You give the vibe.
There we go. No, that's praseodymium. Maybe they changed the names of these.
I'm liking how PO
have to
84
find them.
looks.
Yeah, 84 is giving me a good vibe.
Hold on. I'll look it up in a little bit. I'll try to figure it out. So,
36.
which had only been created in the lab due to their radioactivity. So the radioactive ones, maybe they're kind of down here in the bottom, like the 113 through 118, which looks like their names have been changed. We'll see. We'll figure it out. I'll figure it out. So, yeah, I'll figure it out. So that leads us to our modern day periodic table, exactly like we have it today. Note that you have some complexity over here in the P block because you have several different types of elements. You have your post-transition metals, your metalloids, and your other metals all over here in this square. So they're not all the same in this P block square. Periodic law states when the elements are arranged by atomic number, their properties repeat at regular intervals. That's the periodic part. Did I mention like periodic? Like periodicals is what old people, no offense to old people, periodicals is what old people call magazines or newspapers because they come like once a month or every 2 weeks, or with newspapers every single day. That's the periodic part. So it happens every certain amount of time, like your birthday or the start of a new month. Work by Niels Bohr and Gilbert Lewis on location and behavior of electrons. We talked about Niels Bohr and what he did with the electrons of hydrogen, moving them up and down, looking at the different energy levels. They confirmed the basis for organization of the periodic table and how we thought that it was working.
Yeah. We'll play Arena at Mahia High School at 6:30 p.m. The admission for adults is $4. Students is $2. The gates will open at 5:30. All tickets are going to be sold at the gate on a first-come, first-served basis, and we only have 150 tickets available. So again, the gates will open at 5:30 p.m. The game will start at 6:30 at Mahia High School tomorrow night against Lorraine.
Ooh, Mahia. How far is that? That's pretty far to drive.
I thought it was 4 hours.
Yeah. All right.
6.5.
Yeah, Mahia's pretty far away. But yeah, go support the volleyball team. Playoff time.
Is volleyball like football where they got to go on neutral grounds and playoffs?
I have no idea. I don't think so, but I don't know. All right, hey, let's refocus. Make sure your mask is up, Bobby. So Bohr and who's the other guy? I forgot his name already.
Lewis.
Was it Lewis? Yeah. Bohr and Gilbert Lewis. Good job. Excellent job. Their work with electrons, basically like we talked about with the Lewis dot structures. Yeah, Lewis dot structures. Duh. They kind of figured out that the number of electrons in that outer shell, whether it's 1, 2, 3, 4, 5, 6, 7, 8, the number of electrons in your outer shell is what actually caused the chemical properties and their reactivities. If you had a certain number of electrons, you would combine with a different number, an atom that had a different number of electrons, and everything would kind of work out well in everybody's favor. So that leads us to Glenn Seaborg, who discovered plutonium in 1940 and separated the lanthanides and actinides into their own groups. In that video with Mendeleev, the guy in the video talked about the lanthanides and actinides, the two rows in the F block down at the bottom, and basically said that they're so identical, it was difficult for us to even tell the different elements apart. They're non-reactive. They're all very, very similar. And so he was the first one to kind of separate those into two different groups, the lanthanides and the actinides. Usually shown separated from the rest of the periodic table just to make it fit onto a piece of paper very well. Let's see. And that's it. So the assignment I don't think is very long. It's already opened up. If you have any questions, please let me know. I will help you work through them. Use your little study sheet that you have in front of you. And if anybody needs a periodic table, I know you already have one, but if you would like a colored periodic table, you know where to find them. For those of you at home, please, if you have any questions, let me know. I did post the study sheet to Google Classroom, so if you haven't gone over there already, make a quick trip over there and pick up that study sheet to help you out. Everybody have a nice day and go volleyball.